Welcome everybody to another video of our tutorial. So today we are going to learn chi-square test. So this is an statistical tool which is used to compare observed ratio with expected ratio to determine any discrepancy between observed and expected values of any experiment. So, how can we calculate this chi-square test? So, what is the formula? The formula is this is the symbol of chi, okay, chi-square. The formula is summation of O minus E first bracket within mod minus half third bracket whole third bracket squared, which is all divided by E, where O means your observed value and E means your expected value. And remember that you have to deduct minus half. This half is for years correction, only be used when your degree of freedom is 1. Okay, degree of freedom is what? Degree of freedom is known as DF. Degree of freedom is calculated using this formula, n minus 1. N means the number of observation, so n minus 1 is your degree of freedom. Okay, so remember, before going to calculate any chi-square value, so you have to write null hypothesis. Okay, H0 null hypothesis. So before going any experiment, an assumption is made on hypothesis that this experiment may happen in this way or this way. Okay, so whose validity is tested for a possible rejection on the basis of observations. Okay, and alternative hypothesis, which is denoted as H1, or this symbol you may use. Okay, alternative hypothesis is just a negative of this null hypothesis. Okay, so come now, types of chi-square is mainly 3 types of chi-square are there: goodness of fit, contingency chi-square, homogeneity chi-square. Okay, we will discuss all 3 chi-squares. So first, goodness of fit. Goodness of fit is 4 types: monohybrid test cross ratio, simple monohybrid Mendelian ratio, simple Mendelian dihybrid ratio, and dihybrid cross ratio. Okay, so we can go for some problems so we can understand better. Okay, so first come problem 1. So suppose 2 flowers, you have 2 flower color in P plants. One is purple, another one is white. Purple is capital P and white is small p. Purple is dominant character and white is recessive trait. Okay, now suppose a cross between 2 heterozygous plants produces 160 plants, among which 120 were purple and the rest 38 were white. So if you have to test these results agree with expected 3:1 ratio, then apply chi-square at 5% level of significance. Okay, so this may come to your exam. Okay, so solution. So null hypothesis, simple null hypothesis, you can write these results may fit with 3:1 ratio. Okay, so alternative is that it will not follow 3:1 ratio, it may follow 1:1 ratio. That is your alternative hypothesis. Okay, so now the calculation table you have to do like this: observed value O, expected value E. O minus E within mod. D means O minus E minus 0.5 or half. Why? Because there are two number of observation, only two number of observations. So DF will be n minus 1. N minus 1 means here n is 2. N is 2 means 2 minus 1 is equal to 1. So you know, I have told before, when n minus 1 DF is 1, so you have to do years correction, means you have to deduct 0.5. Okay, so we use this O minus E minus this 0.5. Okay, so only when the degree of freedom is 1, you have to use this. Okay, remember this. Now d square means whole square of this. Now chi-square is d square divided by E. E means expected value, right? So these are very easy. So first observed value, 122 purple flowers were found, is observed, and 38 white flowers were found, total 160. So expected you, how can you calculate? Like this, total is 160 into 3 by 4. 3 means this 3 and 4. How can you get this 4? 3 plus 1, this is 4. Simple, write this. Now you can get simple 120 by calculating this, and this expected value 160 into 1 by 4. 1 this one. Okay, and 4, you know, 3 plus 1 equal to 4. Okay, now 40 expected value. Okay, now come to this column, and now O minus E equal to 122 minus 120 equal to 2. 2 minus 0.5, 1.5. D square means whole square of this. Okay, so you can get this value, and chi-square means 2.25 divided by 120, you will get this value. Okay, likewise you can do the second row. O minus E means here O means 38, E means 40, minus 2 within mod. Okay, now O minus E minus 0.5 means 1.5. Now D square 1.5 whole square. Okay, now D square by E means 2.25 by 40, you will get this one. So summation of these two, 0.017 plus 0.056 is equal to 0.047 0.0749. Okay, so now your degree of freedom is 1, you know, so you have to look for tabulated value. Tabulated value you can get by this Fisher and Yates table, table 4. Okay, your degree of freedom is 1. Okay, and level of significance is 5%. 5% means 0.05. So this value. Okay, this is your 5% level of significance, and degree of freedom is 1. So come. Okay, so your tabulated value is 3.84. Okay, for degree of freedom 1. Okay, right. So your tabulated value is 3.84 and your calculated value is much lower, 0.0749, much lower. Okay, so if your calculated value is lower than the tabulated value, remember your null hypothesis will be accepted and alternative hypothesis rejected. So in this case, your null hypothesis is accepted. That means the data has good fit to the ratio 3:1. So in this way, you can solve very easily any Mendelian ratio. So now come to the second problem. So some of the ratio which do not follow the Mendelian ratio may follow the epigenetic ratio. Okay, in this problem too, in mouse the AV allele has two transposable has a transposable element IAP, which is situated upstream of agouti gene. Okay, the level of DNA methylation at this site determines the coat color of the mouse. So a genetics observed coat color in the breeding of two heterozygous mouse, small a, capital A, small a, and found 120 offsprings. Okay, among which brown color offspring were 30, mottled yellow offspring was 58, and yellow offspring was 32. Okay, brown color means fully methylated, capital A. Mottled yellow means partially methylated, heterozygous, and yellow means unmethylated, small a. So this is the data. Okay, these are the observed data. So if you have to test these results agree with the expected epigenetic ratio 1:2:1, then apply chi-square at level of significance 0.05. Okay, so this is your simple problem. So now come to the solution. So your null hypothesis is very easy. The data will follow the epigenetic ratio 1:2:1. In alternative, you can suppose this may follow an alternative ratio of 1:1:1. Okay, so now the calculation table. So your observed values are 30, 58, 32. These are given here. So now the expected value you can calculate. You know the total is 120 and the ratio is 1:1. Okay, so 120 into 1 by 4, where the 4, 1 plus 2 plus 1 means 4. So that's why in below there is 4. Okay, so 120 into 1 by 4 equal to 30. Likewise 120 into 2 by 4 equal to 60. 120 into 1 by 4 is 30. Okay, so now O minus E means 30 minus 30 is 0. Okay, now D means O minus E whole square, 0 square to 0. Okay, and chi-square D square by E, 0, simple. Now this O minus E, O means 58, E means 60. 58 minus 60 is minus 2 within mod. Square means 2 square means 4. And now chi-square is 4 divided by expected value means 60. Okay, which is 0.066. Okay, now this here O is 32, E is 30. Okay, 32 minus 30 is 2, square is 2 square 4. Now chi-square is 4 divided by E means 30. 4 by 30 is 0.133. Now summation is 0 plus 0.066 plus 0.133, which is 0.199. Okay, So this is your calculated value. This is your calculated value. So here Yates correction is not used. Why? Because here degree of freedom is n minus 1. N minus 1 here n is 3. 3 minus 1 is 2. Okay. So I told you before that Yates correction is used only when and degree of freedom is 1. So it is 2. That's why Yates correction is not done. So now the calculated value is 0.199. Now you have to find the tabulated value. Tabulated value, where is the table? Here is the table. So here your degree of freedom is 2. So you have to find a 5% level of significance. Okay. So this is at 5% of level of significance. The tabulated value is 5.99. 5.99. Okay. So 5.99 is the tabulated value. Okay. And your calculated value is much lower, 0.199. So the null hypothesis is obviously accepted and alternative hypothesis is rejected. So that means the data of the genetics has good fit to the ratio, epigenetic ratio 1:2:1. Okay. Okay. So today this is all for goodness of it. In the next video we will discuss about the other types of chi-square test, that is contingency and homogeneity chi-square. Hope you all understand the goodness of fit problems. So if you like the video, please share among your friends and subscribe our channel. Thank you so much.